It's chemistry and you are watching Chem Science.
In this video, we'll be solving question paper 5-1 or 5-3 of the examination series May-June 2023. So let's start directly with question 1. It's all about partition coefficient. So question 1 says partition coefficient KPC shows the distribution of a solute between two immiscible solvents. KPC is determined by measuring the concentration of solute in each solvent. So here is the whole question. The procedure is also given, and the organic solvent used is ethoxyethane and water. So both of them are immiscible, and the student is asked to find KPC of butane dioic acid between the ethoxyethane and water. So here you can understand that butane dioic acid is a solute, and the two immiscible solvents are ethoxyethane. So you can say that this is an organic solvent, and the other solvent is the aqueous, that is water. So we are supposed to find out the partition coefficient, distribution coefficient of the solute butane dioic acid between these two solvents, organic and aqueous. And here is the expression given where the butane dioic acid, the concentration of butane dioic acid in ethoxyethane upon the concentration of butane dioic acid in the aqueous, that is water, as a solvent. The density of both these solvents are given here, and the process, the method is also given, that what are the different steps to be followed when the performance ethoxyethane partition coefficient is calculated. And you can pause the video and you can read all these steps here, because I'm not going to read it in detail. But let's see that only 30 centimeter cube of distilled water is taken in the separating funnel, and the weigh by difference is 2.81 gram of butane dioic acid is added in the separating funnel, and then the whole process is performed. Let me also read in short that the 30 centimeter cube of ethoxyethane is added, and the separating funnel is shaken, and after the equilibrium has reached, the transfer 10 centimeter cube of aqueous layer in conical flask and titrate with 0.5 mole per dm cube NaOH. So what is done is that after the equilibrium has reached, the 10 centimeter cube of aqueous layer is titrated with NaOH, and in the next step 10 centimeter cube of ethoxyethane is first added with 10 centimeter cube of water, and then it is titrated with 0.1 mole per dm cube NaOH using thymophthalate as an indicator. So what is done in short is that butane dioic acid is shaken between the two layers of equal volume, water and ethoxyethane. Then the concentration of both these layers of butane dioic acid is calculated by titration. So here is the separating funnel, and then we have the questions following it. It says that state whether beaker A in step 7 contains the aqueous layer or ethoxyethane layer. Explain your answer. Now we need to go back and read the procedure. What is beaker A and what is beaker B? Here it says that remove the stopper and open the separating funnel to allow the lower layer to run into beaker labeled A. Now we need to find out that which is the lower layer, and for that we need to find out the density. Here the density, yes, the density of both the substances given, and the ethoxyethane is having a lower density of 0.7, and the water is having a little higher density of 1.00 grams. So obviously the lower layer will be the aqueous, water. So here beaker A is run with an aqueous lower layer. So let's write that beaker A contains aqueous layer. Again, I'm repeating, the reason is that as the water is having a higher density, so it's going to make a lower layer, and as lower layer is run into beaker A, so beaker A contains an aqueous layer. And so here we write the explanation that the water is having higher density, water is having the higher density, and so forms a lower layer. So this is why the lower layer is water, and that is run in the beaker A. The next sub question says identify the piece of apparatus that should be used in step 8 to transfer 10 centimeter cube of aqueous layer. Now if you go back, you will see that step 8 describes the performance of titration of aqueous layer with sodium hydroxide. So if we are performing the titration and we want to transfer 10 centimeter cube of the layer or 10 centimeter cube of any liquid, then it's going to be a volumetric pipette which should be used to transfer the 10 centimeter cube of any liquid into conical flask. So the answer is apparatus is volumetric pipette. So if we go ahead with the next sub question where it says suggest why water is added to ethoxyethane layer in step 9 before the titration can take place. Now here in last step, if we go and check, the ethoxyethane layer 10 centimeter cube is transferred into conical flask, but along with that the 10 centimeter cube of water is also added before the titration was performed. Now the reason being is that acid is soluble, acid is more soluble in water. Acid is more soluble in water. So to transfer all the acid in the water, first we are adding water and then the titration is performed. So acid is more soluble in water, so water is also added in ethoxyethane, and so the titration can be performed properly. If we go ahead with next question B, it says for a 2.81 gram sample of butane dioic acid, titer of aqueous layer is 27.25 centimeter cube and the titer for ethoxyethane layer is 22.50 centimeter cube. The equation for the reaction between butane dioic acid and the sodium hydroxide NaOH is shown here. And the question 1 says calculate the concentration of butane dioic acid in aqueous layer. Now if the volume of water given here is 27.25 centimeter cube, and let's see the concentration of NaOH which is used for aqueous layer here is 0.50 mole per dm cube of NaOH is used for the titration with aqueous layer. So if we add that here, so the moles of NaOH can be calculated with the formula concentration multiplied by volume, and so the concentration is 0.500 multiplied by the volume, that is 27.25. This we are going to divide by 1000 because we need to convert 27.25 centimeter cube into dm cube. So here is the calculation and the answer is 0.0136 moles. That's the answer for the NaOH. Now if we want to calculate the moles of butane dioic acid, I'm just writing acid. So if we'll have a look at the equation, the ratio of acid and NaOH is 1:2. So the moles of acid will be half the moles of sodium hydroxide. So here we need to divide the moles of sodium hydroxide by 2, and so division will give us the answer as 0.00681. This is the moles of butane dioic acid in the aqueous layer present. So now if we calculate the concentration of acid in aqueous layer, we need to have moles divided by the volume. So the moles here we have already calculated is 0.0681, and the volume of aqueous layer which we had taken was 10. That should be again divided by 1000, and so here the concentration of the butane dioic acid we get here is 0.681 moles per dm cube. So let's write that here, the concentration of 0.681 butane dioic acid concentration in aqueous layer only. Now the next question says that calculate the partition coefficient KPC. Now for that we need to have the concentration of butane dioic acid in the organic layer also, that is the ethoxyethane layer also. And for that, we need to calculate the concentration of acid in the organic layer, and we need to calculate the moles first. So for calculation of the moles, we'll directly write the volume. What is the volume which we had used for the NaOH aqueous layer? Is the volume is 22.50 volume of NaOH required during the titration. So if we calculate according to the method which we have used here, is concentration multiplied by volume and then divided by 2. So if we use that directly here, so we get the concentration is 0.1 for the butane dioic acid in organic layer. If we check step 9, the concentration of NaOH used here is 0.1. So the concentration used is 0.1. That should be multiplied by the volume, that is 22. The volume used for organic layer is 22.5. So multiplied by 22.5, again that is divided by 1000, and this whole should be again divided by 2. That is how we get the moles, and this moles should be divided by the volume. Now volume is again 10 centimeter cube divided by 1000. If we calculate the whole calculation altogether, we get the answer as 0.1125. Now that's the concentration in moles per dm cube. Now Kpc, if you want to calculate the Kpc, we need to divide both of this concentration, that is Kpc of concentration of the butane dioic acid in organic layer, that is 0.1125, divided by the concentration of butane dioic acid in aqueous layer, which is 0.681, and so we get the answer as 0.165. Now in few of the cases you might do the reverse also, concentration of butane dioic acid on aqueous layer above, and in the denominator we can take the acid concentration in organic layer. Both ways we can do. Now here I have taken organic upon aqueous, and so for that we get the answer is 0.165, and so let me write this here as 0.165. that's the value of Kpc, that is partition coefficient of butane dioic acid in both the immiscible liquids. The next sub question says here is explain why student is only able to repeat the titration in step 8 once. Now in step 8 the titration is done, and that is done only once. Now let me remind that the total volume of both the aqueous layer and the organic layer was taken 30 centimeter cube in the separating funnel, and for titration if we are using 10 centimeter cube, then we can perform the titration at most twice, where again we can see that both of these full cannot be used, that is full of 30 centimeter of both the layers, both the solvents cannot be used. So here we can perform the titration once only. So let me write that only 20 centimeter cube only 30 centimeter cube of aqueous layer is used during the experiment, and so that's why only once titration is possible. All of the 30 centimeter cannot be used because it might not be able to get it from the separating funnel. And so let's go ahead with the next sub question, where it says is suggest how you would modify the procedure to ensure that the student can repeat the titration in step 8 more than once. So we can say that more volume of the solvents can be used or we can also say that the volume more than 30 centimeter cube should be used. That will give us the better performance, and so more titrations can be performed. A different student forgets to shake the separating funnel in step 5. Describe the effect this would have on the calculated KPC value and explain your answer. Now in step 5, we go back and see what is step 5. Step 5 says that replace the stopper and shake the separating funnel gently. Now if we say that weigh the butane dioic acid into separating funnel and add, so it's going to dissolve more in water first, and then in the step 4 the ethoxyethane was added. So later the ethoxyethane was added, it has to be shaken so that some of the butane dioic acid can be transferred to the ethoxyethane layer from aqueous layer. But if it's not shaken, the butane dioic acid, that is the solute, will not dissolve properly in ethoxyethane. Now if it's not going to dissolve properly in ethoxyethane, you can say that this value, that is the concentration of acid in the organic value, is going to be lower. So if it's going to be lower, the numerator is going to be lower, and that's why the KPC value is going to be lower. So if we go ahead, write here effect on KPC. So we can say that KPC value will be lower. The reason is that the butane dioic acid will not dissolve properly in ethoxyethane, and so its concentration will be lower. So this is the reason that KPC value will be lower. I repeat here, the reason is that if we don't shake, the butane dioic acid will not dissolve properly in the ethoxyethane layer. It won't get transferred in the ethoxyethane layer. So the concentration value of butane dioic acid in the organic layer will be lower, and so hence KPC value will also be lower. Now let's start with question 2, where question 2 says paper chromatography can be used to separate individual amino acids formed when tripeptides are hydrolyzed. So here we are given tripeptides. Tripeptides means, let me clarify again if the students don't know, that tripeptides are the combinations of 3 amino acids. When 3 amino acids join together with the peptide bond, then the 3 amino acids forming one molecule is called a tripeptide. So now if they are hydrolyzed, it will separate into 3 amino acid molecules when they are hydrolyzed. So here the separated amino acids are then chromatographed, that is with the help of chromatography they are separated, and one molecule of tripeptide produces 3 amino acids when hydrolyzed. This is what I've explained you. A student is asked to identify the amino acids formed from the hydrolysis of 3 different tripeptides A, B, C. So here we are given the samples of 3 different tripeptides, each carrying 3 amino acids using paper chromatography. Figure 2.1 shows the results of the students' chromatography experiments, and here is the diagram of the chromatogram given, where the 3 amino acids, the 3 samples of tripeptides are undergone the paper chromatography, and the results of the chromatogram is shown here. If we go ahead with these questions here, the individual amino acids can be identified from their RF values, and the formula for RF value is given. Otherwise also we know the formula of RF value, that is the distance traveled by the amino acid spots divided by the distance traveled by the solvent front. So you can say that's the ratio of the distance traveled by the solvent and solute. Okay, the next sub question here, this sub question A. Suggest why each sample is applied to the chromatography paper using a thin capillary tube rather than a dropping pipette. Now if we talk about dropping pipette, a dropping pipette is a little thicker, will have a bigger drop falling down if we use a dropping pipette. But if we use a capillary tube, it's going to form a very small droplet on the chromatography paper. So here they have asked, suggest why each sample is applied with the thin capillary tube. So what we can say is that with the help of capillary tube, tripeptides, or you can even say these samples can be applied or dropped. Also you can say can be applied in equal amount and uniform way. Now in the MS you might say it's written in short that it can be applied in a controlled way. Here whatever we have written here means the same, so it's not necessary that your answer should be exactly the way it is written in the MS. So here in the MS it's written in the controlled way, which means the same what we have written. Controlled way means it's can be applied. The droplets of the tripeptides can be applied in a uniform way and in equal amount. Okay, the sub question B says, suggest why it is necessary to spray a developing agent over a chromatography paper before chromatogram can be analyzed. Now developing agent can also be called as a locating agent. Now locating agent is generally used when the sample is having the substances which is colorless and the spots are not visible. So here we can say that as amino acids are colorless, so to make the spots of amino acids visible. So if we are spraying it with developing agent, then the chromatography spots will become visible, will actually get colored. So because of that the amino acid spots will become visible, and so we spray them with the developing agent. The next sub question C says, table 2.1 shows RF values for some amino acids in the solvent used in figure 2.1. Now figure 2.1 above was the figure of a chromatogram after performance of the chromatography, and here are the RF values. Now use the data in the table 2.1 to identify the amino acids in tripeptide A. Now let's go ahead in the diagram and find out what are the spots in tripeptide A and how are we going to calculate the RF value. Now as we have already seen that the formula of RF value is the distance traveled by the amino acid upon distance traveled by the solvent. So if we talk about the first spot or the topmost spot, we can see that it had approximately 5.5 distance, and the distance traveled by the solvent front is 7 centimeter. So we talk about the first RF value. Our value should be 5.5 divided by 7, which is approximate equal to 0.78, or you can say 79. This is approximate value because the value is quite bigger in the decimals, but we have shortened it with 2 decimal places. Now if you talk about the second spot, if we count from the center, it is approximate 3.6 or 3.7 we can say. So suppose if we take it is 3.7, the RF value should be 3.7 divided by 7, which is approximately equal to 0.53. Now if we talk about the third spot, which is at the bottommost, I would say it is approximately 1 centimeter cube. So RF is 1 divided by 7, and so RF value is equal to approximately 0.14. So here are the three values: 0.79, 0.53 and 0.14. Now if we compare it with the values which is given in table, the 0.14 is lysine, then 0.5 approximately is tryptophan, and 0.73 leucine. These are the three which we have approximate values here, which we have got the RF value, calculated the RF value above. So identifying the amino acids, we can list here the amino acids as lysine, tryptophan, and the third one is leucine. So these are the three amino acids present in tripeptide A. Now if we go ahead with the next sub question, it says suggest why the hydrolyzed sample of B produces only 2 spots. So again, if you go back and check the diagram, you will see that the only 2 spots are produced for the sample of B, and this is possible only when there are 2 types of amino acids present in the tripeptide B. Now if we are saying tripeptide, there should be at least 3 molecules of amino acids, but if the 2 spots are produced, that shows that there must be one of the amino acid which is repeated or which is used twice. So you can say that only 2 types of I won't say there are only 2 amino acids present. I would say there are 2 types of amino acids present in B. 2 types of amino acids present in B. That means one of the amino acid is repeated and used twice. So let me be very clear, there are 3 amino acids, but one of the amino acid is used twice. Okay, next sub question says 2 of the spots from the hydrolyzed sample of C overlaps. State the reason for the overlap. So to understand that, let's have a look at the diagram again, where it says that 2 of the spots are overlapping and there is one spot which is little above the 2 of the overlapping spots. So in that case, what I would say is that the RF value of 2 of the amino acids are similar. I won't say the RF value is same, but I would say that the RF value of 2 amino acids are just similar, means the value might be closer to each other. So the RF value of 2 of the amino acids are, I'm writing similar. Remember, I'm repeating, I won't say it is same, it is similar. The value is similar, closer to each other. You can write the value is closer. So that might be the reason that they are very close to each other or they are overlapping. Now here the sub question here says suggest an improvement to the method that would allow the overlapping spots to be distinguished clearly. Now if we want to distinguish with it clearly, it should be separated more. Now to make it more separated, we should allow the chromatography to perform for a longer time. Now this is possible only when we use a longer chromatogram. So we can write one of the reason as that use a longer chromatography paper. Use a longer chromatography paper. Use a longer chromatography paper. Or you might also say that use another solvent where the solubility of these 2 amino acids differ. So there may be one more reason, that use a different solvent. Use a different solvent where the solubility of the 2 amino acids might differ more, and so they are separated more. So here ends the question 2, which was very short about chromatography paper. The experiment of chromatography was described in a very short way, but yes, you might say this question was quite easy. The next is question 3.